Okay, we continue the discussion about the inner product space. So for inner product space, we can introduce the concept of basis. First, we have an inner product space with the inner product defined. Let's say we have a set of elements or set of vectors in this space. And this A denotes the index set. The set itself is the S. We call this S a basis. Basis of X. If for any element in X, it can be written as a linear combination of these elements in S. And moreover, the combination coefficients of this linear combination or linear representation is given by this. It's just I can take the inner product of X with each of these basis element. Okay? And this coincides with our common interpretation of basis. You can get a set of orthonormal basis, orthonormal set, so that we can just rewrite X in terms of this linear combination. Okay? And the coefficients are given as the projection onto each basis. Okay? And there's a name for this. This is called the coefficient or Fourier coefficient. For of this X with respect to E alpha. Okay, so we showed in real analysis that there is a so-called Basal inequality to bound the sum or the series of these coefficients using the norm of X. Okay, and this is given by the so-called Basal inequality. Okay, so what this Basal inequality says is that, again, we start with an inner product space. So if S is an orthonormal set, not necessarily a basis, and any orthonormal set, or this S can be written as again, this is E alpha, where alpha is from the index set A. Then for any X, we know we take the series of the squared Fourier coefficient, not necessarily Fourier coefficient, just projections of X onto each of this E alpha. This is going to be less than or equal to the norm of X squared. Okay, so this also holds for in the case where S is a basis, but it actually holds for general orthonormal set. I'm going to show you that the proof is something we have done before, but what I'm also going to show you here is that we want to look at the terms. If you have this orthonormal set, want to check the terms. It can be this can be non-zero for at most countably many E alpha. Okay, so we can for each of this E alpha we can take the x inner product of x and this is E alpha. I'm going to show you that this can be non-zero or for only countably many of these E alphas. Okay, so let's first show this inequality. Let's look at any finite set of this set S. Say we have just collected n of them, n elements from S. Then we can check. First of all, when we take the norm of x minus x ei I from 1 to n, so it's just like a linear combination or representation of x using just this, where the coefficients are given by like the Fourier coefficients before. And since this is not necessarily a basis, so I know that at least this is greater than equal to 0 since it's a norm. This is the norm, right? And on the other hand, we know that we can expand this or break this square. We can rewrite this as x minus the sum of x ei, also x minus sum x ei. Okay, and then it will be very easy to show that this essentially just become the norm of x squared, and then you have two interaction terms, this times x, and also this x times this, and then finally you have this times that. But all these three terms are the same, so you essentially just subtract one of them, and that becomes minus sum of I x ei squared. Okay, it's pretty easy to show. And this, since this is greater than or equal to 0, we know that the Basal inequality holds, which is the one here. Okay, so that's for the Basal inequality. But I want to make as I mentioned earlier, I want to show you that there cannot be more than, there are at most countably many of these EIs that could make this coefficient non-zero. Okay, then why is that? Let's consider the set, say AK. So what this AK is, it is a set of the index alpha such that the inner product of x and the E alpha is between 1 over k, 1 over k plus 1, and 1 over k. Okay, this is for each AK. So let's take an absolute value. Okay, and this is for k greater than equal to 1. So it's all the natural numbers. And also I can define A0 just to be the index set such that the x E alpha is bigger than 1. Right, you can do this. So now let's look at for any alpha, it has to be in one of this. So I know that the alpha, the set A, is just the union for k from 0 to infinity of this A k. Right, that's what I know. All the elements in S must be in, every element in S must be in one of these AKs. Okay, but I'm going to claim that for each of this AK, it can be at most countable. Why is that? So claim AK is at most countable. The reason is, if not, then we look at the k. There exists countably many index or indices. Say this, I call it AI alpha I, let's say, such that the x EI, this is bigger than our E alpha I. This is bigger than 1 over k plus 1, right? And so I can, since I have countably many of them, I can just keep adding them. So I know that the sum of this x E alpha I, if I take the square, I know that it will be eventually going to be bigger than, it could be actually infinity, because each one of them is bigger than 1 over k plus 1. So the sum of them will be infinity. And this is a contradiction to the fact that no matter how you choose the orthonormal set, this x square is always bigger than equal to this, right? Because if this is going to infinity, then you know that up to some n, you make this even bigger than this, and that cannot be. You cannot have positivity from here, right? Since this is approaching to infinity, so you know that for r large enough, this will be bigger than the norm of x squared. So that's why each of this must be countable, right? Has at most countably many elements, okay? And that's why you have countably many of this, so that's at most countable. Okay, so although you can have a S that is uncountable itself, and it has uncountably many orthonormal elements, but when you project this X to the basis here, then at most countably many of them can be non-zero. Okay, so that's the statement here. Okay, so let's consider a corollary of the theorem here. Actually, because of the orthogonality, we actually can write out the norm here, because this will be able to show that on the one hand, I know this is actually just this, and this actually tells us that when we have this basis or orthonormal set, we actually can easily distinguish or compute what this normed distance is. Easily compute what this normed distance is. So let's say let X be a Hilbert space. Let's E alpha is orthonormal set. Then for any x, we know there is, you take the expansion or linear combination of such thing. We will know that this will be this must be in X as well, and also we take the square distance of this X and this linear combination. We actually can get that this is just equal to X squared minus the squared, the sum of squared coefficients. Okay, we actually have this. Okay. So on the one hand, we know that for every fixed x, we don't really have to write out everything here because there are at most accountably many of them with non-zero coefficient. So actually, we know that by this theorem above, we know this sum is essentially just a countable sum, or at most a countable sum. Okay, this E alpha S form a countable subset of this set as here. And from here, we can see that by the Basal inequality, this is convergent. This series is convergent. The reason is no matter how many finite many of them, so you just extract finite many of this, this sum is less than, so you know that for any finite many of them, this x e alpha I, this is going to be less than that, right? So when you make n approaching to infinity, this is still less than or equal to x squared. So this, if you change it to infinity, is still true. Okay, and that means this is convergent because every term is non-zero, is non-negative, and the sum is this is the series of a sequence of non-zero or non-negative numbers. Okay, so it's convergent. Well, it is convergent means that, well, if I look at any k, I just look at the partial sum from k plus 1 to k plus p, then it doesn't matter what this p is. As k goes to infinity, I know that this will be approaching to 0, right? As k goes to infinity. And it doesn't matter what the p is, as I said. P is any integer. And this tells us that if we define let x k denote the partial sum for this x and the e alpha I, then we know that, well, on the one hand, I can see this this xk is a convergence sequence. The reason is we look at xk plus p minus xk. apparently this square is just the square above, okay, just this. And I know that goes to 0 as k goes to infinity and for any p. So this tells us that this xk is a Cauchy sequence. It's a Cauchy sequence in X. But X is a Hilbert space, so it's complete. And that means there exists a limit. Okay? And it's actually pretty easy to show that the limit can only be the X itself. So xk is this I from 1 to k xe alpha I, and we know that's going to approach to, according to that definition, it's just approaching to this xe alpha I. Okay? And this we know that it is in X. Okay? On the other hand, we can see that we look at the difference of X with any sum I can see here. X e alpha I, e alpha I. Let's look at the inner product of this and this sum. We know this is going to be 0 because this is a linear combination of the E alpha i's using the orthonormal set. And these are the coefficients we had from the Fourier coefficients. When we take the inner part of this, we'll be able to show that this is equal to 0. Like I can show that this is just a x. If I split the first term, this will be just a sum. Right, x e alpha I, e alpha I, and we also have the same of them. Right, the point is that when you take the inner product of x with each of this, then you can pull this thing outside, and then essentially you just have the sum of, you still just have the sum of I, which is x e alpha I, and again another e alpha I, so it's just this square, and the second term is the same. So this is essentially just equal to 0. Let's remove this. Right, this is just equal to 0. And that means these two things are orthogonal to each other. Well, with this, we can show that when we take the expand this square, this is from 1 to infinity. We expand this, we'll see that it's just the same thing here, and then it's just equal to x squared. And again, we have two interaction terms, and then the last term, which is just the square, it's just this one here. Okay, and so essentially we just have this minus 1 to infinity, which is e x e alpha I and e alpha I here. Sorry, it just squared. Okay, and that's why we have this identity here, because we know that this sum essentially is just a countable sum, even if A itself is uncountable, and also here this is just a countable sum, and that is actually what we derive from here. Okay, so it's just the equality for the Basal inequality actually holds. Okay, this actually has a name called the Basal equality, and if we have a basis which is countable, then we actually can have this Basal equality holds, which is given by the following theorem. Actually, this is more than that. We are going to show in which case S is a basis. There's a sufficient necessary condition for that. Let's say we have a Hilbert space. And again, S is also normal fat. Okay, suppose we have a Hilbert space, and we have also normal set S here, which could contain uncountably many elements right here. And then we're going to say that the following three statements are the same or equivalent. The first one is that the S is a basis. Okay, remember that by that we mean that every x can be written as this x e alpha alpha is from A, right? That's the definition for S being a basis. Second is that S is complete. Remember that for this, S is complete means that if the x e alpha equals 0 for any alpha, implies that x itself is 0. So the definition for S being complete. The third one is the Basal equality. Which says that Basal equality holds, which says that every x, its normal square, is just the same as you take the square sum of the squared coefficients. Okay, we're going to show that these three are actually equivalent. Okay, we first show from 1 to 2. Suppose S is a basis. We want to show that it's a complete. Okay, if not, so you prove by contradiction. If not, then that means there exists some x that is non-zero. Such that the x e alpha is 0 for any alpha. Okay, and if this is true, then we know since the S is the basis, we can rewrite x as a linear combination of the basis with these coefficients. But this means that this is equal to 0 since each of this coefficients is 0. So this means that x is equal to 0. And that is a contradiction to the statement here, which says that x is non-zero. Right? That's a contradiction. From second to the third. Suppose we know that S is complete. We want to show that the Basal inequality holds. Okay. If not, then we look at this x minus the sum for alpha x x e alpha. Let's look at this. We know that this will be equal to, because S is complete, we know that this is always equal to that, right? We know that this is always true and is greater than 0. Because we know that this is always greater than equal to that. And if this equality doesn't hold, that just means this is greater than that. Okay, and this is greater than that. And that means this is greater than 0. And this is greater than 0 means that this one here itself is a non-zero vector. So I call this vector y. Okay. I denote this by y. So I know that y is non-zero. At the same time, as we showed before, we take the inner product of this y and this. Actually, when we take the inner product of the y and each of this e alpha, what we will get is the x minus the sum. Sorry, here is x e alpha. Take this inner product. Okay, and now I can split them. This becomes x e alpha minus the sum of alpha. So I use alpha prime here. X e alpha prime, e alpha prime, e alpha. Because all this e alpha, they are orthonormal. Right? So what I have is only one of this sum. Take the inner product of this. There is only one of this sum is non-zero when we take the inner product with this. Right? And that term is essentially just the e alpha. And then we'll have the x e alpha here. So this term here is just x e alpha times e alpha. But this one here is equal to 1. That's why I actually have this and this. So that means this is equal to 0 for any alpha in A. Okay? And for any alpha in A, I show that this y e alpha is equal to 0. That just means the y is equal to 0. But that is a contradiction to the fact here, or to what we got here, where y is non-zero vector. Okay, so that's the contradiction. And lastly, let's show from 3 to 1. Okay, suppose we know the Basal inequality holds. We want to show that S is a basis. So we actually have the sum here. I know that this is just the norm of x squared minus the sum of x e alpha. Right? Because the Basal inequality holds, this should be equal to 0, and that just means that this one has to be equal to 0. Okay, for any x, I know that this is equal to 0. It just means that x can be written as a linear combination of the E alpha. And this means that the E alphas form a basis. Okay, and that shows 1. Okay, so you can see that these 3 are actually equivalent. We say that this S as a basis means that it can be every X can be written as this in this linear combination, and it's equivalent to saying that S is a complete as the second one, or you can just verify that by checking the Basal inequality. If this holds, then this also means that S is a basis. Okay, but remember that S itself could be uncountable. Okay, it could have uncountably many elements. But when you take the inner product of any fixed X, you give any X, you take the inner product of X with those bases, only countably many of them. At most countably many of them could be non-zero. Okay. Let's look at an example, and think the most famous example would be the actual Fourier coefficients, or we interpret it as a Fourier transform. Say we have a function or function space, or the square integrable function from on the interval 0 to 2 pi. Then we can consider the basis ek, and what this ek is. Each of this ek is a function in the R2 space, and it's defined as the eikt over square root of 2 pi. Right? The k is an integer. An integer. Okay, so these are countably many of them, but the k actually can be from negative infinity to positive infinity, all the integers, positive or negative. This is actually a basis. Okay. And in this case, the Fourier coefficient is the, say we take the inner product of f and the ek. It's actually just the integral from 0 to 2 pi u of ikt. Sorry, it should be 1 over 2 pi here, and f of t dt. Okay, so this would be the Fourier coefficient. Okay, I think it's negative. It's negative here. Okay, for any FEL squared or L2. Okay, so that's one typical example, and also this will be a trivial example, the L2 space, which is just all the sequences, right? Xi, where each of these xi is in, say, in R. And also the sum of them, the sum of square of them is finite. Okay, this is also easy to get the fundamental basis, which is just the ek, where you have every term as 0, except the case 1. This is the case 1. Okay, so this is in R2, and this is a basis, as you can see. Okay. So there's something that you probably have seen many times, called the Gram-Schmidt orthogonalization, which means that when you have a linear independent set, you can make them orthogonal and normalize them, so they can form an orthonormal set. Right? So that's just something that you probably have seen many times before. So I have these vectors that are independent. These are all from X, from Hilbert space X, Hilbert, or even just inner product space. It will be no. They're linear independent. I should say clearly that's linear independent. Okay, and that means none of them can be written as a linear combination of the others. Okay, and we can do a Gram-Schmidt orthogonalization. And what we can do is we start from the first one, and then we set the y1 to be our e1. For x1, we can define the e1 to be the x1 over the normal of x1. We know that they are linear independent, so none of them can be 0. So we can just get the e1 here. And for e2, we're going to first start with the y. So the y2 is equal to x1, so x2 minus the x2 e1, which is the one we just got, then this. And then we normalize it. Okay, so maybe I can make it consistent. I will start with the y1, which is just set to x1, and then I have y1 divided by the normal y1. Okay, for y2 I do that. So you can continue doing that. You have y, so you have when you have yn, you have the xn minus the sum of the xn and all the previous spaces you already obtained. The I is from 1 to minus 1. And then you just set your en to be yn over the norm of yn. Okay, you know that all the denominators must be non-zero because none of them can be written as a linear combination of the previous ones. So that means there's no way to get a 0. You will never get 0 y's. Or never get any y as 0. Okay, so just continue doing that, and then this thing will be a basis, or this will form a basis. A orthonormal set, sorry. Okay, you will form orthonormal set. Okay, that's the Gram-Schmidt orthogonalization. We talk about homomorphic between Banach space. Means that if you are concerned about the algebraic structure of the two spaces, they are actually the same. And also consider isomorphism between Banach space if the norms are kept after the transformation. We call the two space isomorphic. And this can be extended to inner product space as well. So suppose we have two inner product spaces. If there exists a isomorphism, I should say homomorphism. And you know that by this we mean for any element in x1, alpha, say alpha beta, alpha tx plus beta ty, for any alpha, beta in R, or in K if you're considering possibly complex numbers as coefficients, and also xy from x1. If this is true, then we say, and also T is a bijection, then we say that T is a homomorphism, right? If this homomorphism also satisfies that for every x and y in the x1, the two norm of tx and ty, because after the mapping, these tx and ty are in x2 now. If this is always equal to xy in the first space for any x and y in x1, then we call T an isomorphism. This means that this keeps the distance or the inner product as well, not just the algebraic structure, also the inner product. Okay, so in this case, we can just identify these two inner product spaces because all the behaviors will be the same. Okay, just like a side note of that. Now we consider, we say that some additional property of a Hilbert space. For example, we can consider the dimension of a Hilbert space. We can consider the if a Hilbert space is separable or not. Okay, so for example, let's say let X be a Hilbert space. Then one thing we know is that, I would say, yeah, one thing we know that is X is separable if and only if X has a, or any basis of X is at most countable. Okay, either finite or countable. So we recall that what do we mean by separable space? It means that it has a countable dense subset. Right? X is a separable if it has a countable dense set. And the basis we just introduced, S is the basis if every X can be written as a linear combination of the elements in S. Right? If this basis is at most countable, contains at most countable many vectors, then we say this basis as at the most countable. So these two are actually equivalent. That's one thing. The other thing is about the dimensionality. When we have a basis, then the we said if X is separable, that means that S is either finite or countable. Okay, then X is isomorphic to just Rn if S has n elements, or the basis S has n elements. And if S has countably many elements, then this S is isomorphic to L squared. L squared is the one the sequences which are square summable. Okay, this is the case where S is infinite. Okay. So if X is separable, then we can consider the dimensionality, and actually either one of these must be true. Okay, let's show the first one. Okay, I want to show that X is separable if and only if any basis S is at most countable. Okay, let's show this direction first. Suppose that X is separable, then it has a countable dense set. Okay, we have a countable dense set. We denote it by the xk. And now from this, we can extract a linear independent set. How do I get this subset? We just go through all this xi. So we start from x1, then go to x2, x3, and every time we see if this xk can be linearly represented by the previous x. So we have x1, x2, xk minus 1, xk. Okay, so for example, when we are at this point, we'll see if xk can be written as a linear combination of these things. And if they can be, then I will just discard it. If it's not, then we'll keep it, we'll put it in the set of y. So that's how I can form this, the y case. It's like a sub set or subsequence of this x, so that everyone, all of them are linearly independent of each other. Okay, it's a completely linear independent set. Okay, so this is how I got this linear independent set of yk. And now once we have the yk, we can do the Gram-Schmidt orthogonalization because I have a linear independent set. It's linearly independent. They can form the basis or form an orthonormal set out of it. Right? And then from here, we can see that. So now let's just say how this is how I got this orthonormal set. Apply Gram-Schmidt to this yk to obtain an orthonormal set ek. Okay, I'm going to show that this ek is actually basis. The reason is, you look at the span of xk. Because of the way we constructed this or extract this yk, we know these two are the same. Because the yk is essentially just taking all the linear independent ones, removing all these redundant ones. We can have this. And also the ek's are constructed by the Gram-Schmidt orthogonalization from yk, so this is also equal to the span of the ek's. Okay. And if I have this, then we take since all these spans are the same, I can take the closure of them, they will be still the same. Right? So we have that. And now remember that the xk is a countable dense set in X. And if we take the closure of this will be essentially just X. Okay, and that just means that this is X as well. It also shows that there's no element, no non-zero element that can be perpendicular to this span. And that also means that this EK is actually a basis. Okay, because no any element that is perpendicular to this must be 0. Okay, so this implies that if x is perpendicular to the span vk, then x is equal to 0. And this means that it's complete, and also that means that the EK is actually a basis. Okay, so that's one direction. The other direction is, suppose we know that this basis of S of x is at most countable, then we want to show that it is a countable dense set. So for simplicity, that the S is countable, then the S is countable means that I can rewrite it as just this. Okay, and I want to show that this x, the set x, or space x must be separable. Why this separable? Let's see, any x, I know that in this case, any x can be written as this way, right? It's x e alpha ek, sorry. I know this. Every x can be written in this way, so essentially my x is just that. Where this what I should say this. That's every x can be written in this way. Okay, so this is my x. Well, now I just need to check if this forms a countable. What should I say? See, in this way. This is better. So because it's as I've said, S is a countable basis, then we know that every x can be written in this way. And now let's consider this set, which is countable say AK, EK, or the AK, or if we consider the AK to be possibly complex numbers, then we will see the real part of AK and also the imaginary part of AK if they are in Q. Then I know that there are countably many of these AKs, right? Possible AKs, because they're taken from a countable set. And this one itself is countable. That means I can have at most countable such kind of combinations, since this is the countable sum of countable many choices. And I want to argue that this is actually dense in X. The reason is that this for any coefficient, I can use a sequence of a real, actually the real valued, the complex numbers with the real value, complex numbers will with the rational valued real and the imaginary part can be, we can all use this to approximate that, right? So you can see that this will form a countable, dense set of X. Right? Countable is because these coefficients are actually from Q, and it is dense because every complex number can be approximated by some number AK like this. Okay, so it's a countable dense set, and that verifies this direction. Okay, so that means if it's separable, then the x, the basis x is either finite or countable. And in this case, we can define the dimensionality or dimension of this x. And the purpose of doing that is that we can identify the x with some simple sets like this, or simple space. For example, if S is finite, that means we can find a basis with only E1 through En, and then we can make an isomorphism between X and this Xn. Okay, and also if S is infinity, we can just make an isomorphism from X to L2. And let's just say the second case. It's probably non-trivial. Suppose that this is infinity, then we just know the S is equal to K, right? K is from natural numbers. Then we define this T will map every X. You know that X can be written as the X EK EK. Right? I can just map this X. This is an element in X, and it's mapped to some element in L2, and apparently I'm going to map this element to xe1. This is my first number, xe2, right? So on and so forth. Okay, and then it will be easy to show that this T is a linear. This is a linear and bijective. Okay, it's easy to show that T is linear and bijective, so that means T is a homomorphism. And the more importantly, I want to show that T is an isomorphism, which means I will keep the inner product. So how do we do that? Let's just compare after the mapping. I have the Tx. So first of all, when I have the x and y itself, for this x, say I can rewrite it as a k e k. So y I'm going to write as the bk where this ak is just the inner product of x and the ek, and also this bk just a y ek, okay, for any k. Now the inner product of this, we know that's still in x. This is supposed to be just the sum of ak ek 1 to infinity, and also the sum of bk ek. And because the EKs is a basis, they are orthonormal, so it's pretty easy to show that it's essentially just the sum of AK, BK. Okay, if these are real, if it's a real valued or real Hilbert space, if it's complex valued, then you just have that. Okay, but either way, this AK, BK is just, you can treat it as these A1, K, that's B1, BK. Just treat it as inner product of this in the L2 space. But this, according to our definition of T, this is just Tx. This is just the Ty. So that's just essentially just Tx, Ty, L2. And that's why it is our isomorphism, right? That's why the T is isomorphism. Okay, so so you can see the structure is getting clear, pretty clear for Hilbert space. We actually have, so for Hilbert space, because the inner product is defined, so we can have like 3 possible cases. One case that is X is isomorphism to some Rn. So basically in this case, we can identify X and Rn, and that makes everything simple, right? And then we can also consider when the basis of X is countable, then we know that it's isomorphism to L2. And then we'll have another case. In this case, so these two cases, we see that the X is separable, as we showed earlier. Separable. In the last case, it's not necessarily separable. And this is the case where we may have a basis that is uncountable. Okay, and this is there are many examples of this. So, for example, it's just one of the examples. So we have X equals to L2R. Okay, this is not an L2 space like this one. Instead, it is the set of function f that is, say, from R to R, and f is non-zero at most countably many points in R. So f x this is non-zero for at most countably many x in R. And also, since I'm going to define norm, I'm going to define the norm is less than 0. And what this norm is defined as the sum of f x in R. This is squared, and then take our square root. This is going to be the norm I'm using here. Okay, this is because I have at most countably many non-zero values. So when we take the sum here, it's actually reduced to a sum of at most countably many terms. So this sum makes sense. It's not taking sum over uncountably many terms. Okay, so this makes sense. And this is how I'm going to define the norm. And if this x is a set of functions f like this, then we can easily show that the x is not separable, meaning that it doesn't have a countable basis. The reason is this x is easy to show that this is a easy to show that this is a Hilbert space, because we can actually get the integral product from this norm. So if I have f and g, then we can just define this to be sum of f of x, g x, x in R. Okay, because both of them is 0 except for countably many values or countably many terms. So this 2 is non-zero for at most countably many terms. So this is the inner product, which is okay, and that is the norm induced by that. And then it's easy to show that X is an inner product space, and also we can show that it's complete. So actually X is actually a Hilbert space, but it doesn't have a countable basis. Say, for example, I have a basis, or it has a basis that is uncountable. So let's say I have this EX as an element in X. So what is the X is? Just a function from R to R. And it's defined as, for any y, it will take the value 1 if y is equal to x. It will take value 0 if not, if y is different from x. So you can see that if I want to use this to represent all the functions in x, then I have to use all the possible x, right? So this is actually EX, where x is from R. This is actually our S, and apparently this S is not countable. Okay, so this is the basis, but it's not countable. And that's the third case right here, where the function x is not separable anymore. But although it's not separable, or S here is uncountable. But when you express any term or any x or any function, say here, or x or f, any function in here, we want to write this f in terms of a linear combination of these things. You only finite many of them is non-zero. Okay, as I said before, we have this. But only finite many of these things could be non-zero. Okay, that's still true. Okay. So I guess this is what we almost all everything we need to know about the Hilbert space. That's the topic, which is the kind of parallel to the Bachner space. We can also consider the projection of some point in the Hilbert space to some set, or especially convex set. And in this case, since we have the inner product, we get lots of the structures of this Hilbert space. And that actually gives us more information about the projection point. Okay, so here we're going to consider the projection problem one more time for Hilbert space here. So again, this is like we have a convex set, say C, and then we have a point, which is outside, and I want to see that what is the projection of this X onto this convex set. And this is usually more useful in practice, since especially when you're working on Euclidean space, you know that it's not automatically a Hilbert space, since we have inner product structure on that. So when we consider the projection, we know that the definition is we take the infimum of this where y is from the C. Okay, so the question is, if I consider the projection, is there a projection point, or if the projection point exists, and if it exists, if it's whether it's unique or not, right? That's our question. So we have a point X which is outside of a closed convex set C here, then everything is entirely in the whole space X, which is a Hilbert space. Then the question is if the projection point exists and if it is unique. Okay, so since it's a linear space, we can always move things around. We should say that I have point X here is actually 0. Let's say we do a projection of 0 onto the C and see if the solution